So our last topic for the semester is columns. And what we're going to talk about today is column buckling. When we're talking about columns, we've talked about compressive stress, which is usually the force that columns are under is a compressive force. And generally the compressive stress, it's really hard to overload a column in compression. It can take a tremendous amount of load. They usually have a pretty large safety factor. And this large safety factor is for a couple of reasons. One is that it's a larger area of effect. You know, if a single beam fails, it's usually a pretty small area that's affected that's going to have some issues. If a column fails, there's usually a couple of beams or a system that is supported by it. It can usually affect a larger area. The second reason that there's a larger safety factor is because of unexpected changes, uncontrollable conditions. All of our calculations are done assuming a perfectly straight column. Well, most materials are not, especially if they're wood, they're not perfectly straight. They get some sort of a bow in them as the wood dries, or metal will warp over time. It's not perfectly straight. Therefore, that's going to weaken that column, make it more likely to buckle. The columns, especially if it's like in a basement supporting a floor beam, it's going to get bumped. A column that's at its limit, holding just fine, but at its limit, if it gets bumped from the side and causes it to be pushed over, well, that's just giving it that little boost in the direction of buckling, and it will buckle. So you have to allow for living conditions, too, of what's going to happen to that column. Is it going to get hit? Is it going to have an unexpected sudden load change from above? Even though it doesn't put it over the limit, but a sudden load change can cause, like the stress risers we talked about, it can cause the vibration in the floor being translated into that column, any sort of vibrations in that column can cause it to displace enough to affect the buckling when there's a sudden load change. So all sorts of things like that have to be considered. So we have usually pretty much a larger margin of error safety factor. So then, of course, we have buckling, is what we're trying to discuss here, dealing with the buckling. And all that is a sudden lateral displacement, horizontal displacement. And generally, it's unstoppable. Once it starts to buckle, it's going to go. It's going to go complete failure. There's no beam sagging and starting to crack type deal where you have with beams. Once the post starts to buckle, it is usually catastrophic. That's one of the other reasons for the larger safety margin. If you work around houses long enough, you're going to find beams that are cracked and sagging and need to be replaced. You'll almost never find a post or a column that's damaged without failing. So you were using for short, we divide our columns into two categories. We have short and long. In a short column, buckling is not an issue. So all we have to worry about in a short column is our standard stress formula. If the critical stress, which is going to be the load divided by the cross-sectional area, and it has to stay below that critical stress level. In a long column, now we have to worry about buckling. Now there's all sorts of things. First of all, we have to define what is a long column, what is a short column. To do this, we describe slenderness of a post. Now we have a couple of slenderness type ratios out there that we've used. One of them is that radius of gyration. Remember, the radius of gyration, r, is equal to the square root of the moment of inertia divided by the cross-sectional area. When we're dealing with a column, that would be the smallest moment of inertia. So let's say we have a rectangular post, a 4-inch by 6-inch. Well, the moment of inertia in this direction will be larger than the moment of inertia in that direction. So it's going to be this axis here that we'll use the moment, because that's going to be a smaller moment. It's the smallest moment of inertia. And then the area, of course, is usually found as an average area, or if it's a significant change in area, you do take the area at the smallest cross-sectional area. So that is one of the ratios that kind of describe the slenderness. But then we actually have what is called a slenderness ratio. And the slenderness ratio is the length or the height of the column in inches divided by that radius of gyration. L is the length or the height in inches. So, there are two formulas that we can look at. The first formula is actually the Euler formula. Now, if you're anything like me, the first time I saw that word when I was in engineering school, I was pronouncing it Euler. It took me like 3 days to figure out who's this Euler that they're talking about. It's the Euler formula, and it is to find the critical load on a post. On a post or a column. That critical load is equal to pi squared times the elastic modulus of the material times the smallest moment of inertia, so the moment of inertia in the direction that makes it the smallest value, divided by the length of that post in inches squared. So let's say we have an 8-foot tall, 3.5-inch square post. Let's find its critical load. Its critical load will be pi, so 3.14 squared, times, it's wood, so we're going to assume elastic modulus of 1,600,000. Times, we need to find the moment of inertia. What is a square post? So it's got the same moment of inertia in either direction, x or y. It's going to be 3.5. We'll go with 3.5 to make it easier on the calculator. 3.5 times 3.5 squared over 12. Or not squared, cubed over 12. So 3.5, we're just going to go to the 4th power and get it over with. Divided by 12 gives us 12.5 is the moment of inertia. Over L, it's 8 feet, so that's 96 inches tall, and that's going to be squared. So 3.14 squared times 1,600,000 times 12.5 divided by 96 squared. So 21,397 about. Or 21,400 pounds approximately. That's our critical load. So if that beam is supporting more than 21,000 pounds, it's in danger. Let's take a look then at critical stress. Critical stress actually makes a little bit more sense. It's found from the Euler formula. I have to double check something because it looks like I missed something in it. No, I did not. Okay. The critical stress is similar to the Euler formula, but what it is this. It is still pi squared times the elastic modulus, but then it is over the slenderness ratio, which is just L over R squared. Now, if you think about it, R is the square root of I over A. So R squared, this would be L squared over R squared. R squared is just I over A. So this actually is the moment of inertia from up here, and then we're just dividing by the cross-sectional area is all we're doing. So we're just taking that Euler critical load formula, dividing by the cross-sectional area of the post. And let me prove to you that that is just exactly what's going on here. So our radius of gyration, the area is going to be 3.5 squared, which is what, 12.25 square inches it looks like? So the radius of gyration, R, is the square root of I, which was 12.5, or 12.25. So we're going to get just over 1 for our radius of gyration. .01 is our radius of gyration. So for their formula here for the critical stress, it's 3.14 squared times the 1,600,000 over L, which is 96, over 1.01 squared. So 3.14 squared times 1,600,000 divided by 96 divided by 1.01 squared. So 1746 PSI looks to be our critical stress. If we had taken this 21,400 pounds here and divided by the cross-sectional area of 12.25, we would have got 1746. So it really is simply just the critical load divided by the cross-section area. So then how do we know, excuse me. So all we need to know is that critical stress then, and we also need to know compressive stress on a post to analyze it. So let's say we have a post. It is a 5-inch by 8-inch post, and it is holding a 40,000 pound load. Is it going to hold? Well, the first thing we're going to do is we're going to do compressive stress. The compressive stress, remember, is the load, 40,000 pounds, divided by the area. Well, 5 inches by 8 inches is 40 square inches. That's going to be 1,000 pounds per square inch, PSI. Well, for wood, we go back to our table again. Come on. My book's a mess here. For a post, we're allowed a compressive stress of 1,000 PSI. So we are right on the limit for compressive stress. That compressive stress does involve a little bit of a safety margin. So we're okay. We're not going to be worried about it. But we are right on the limit. So that means buckling could be an issue. So let's figure out, I usually, rather than doing the critical stress for buckling, I usually use the critical load, the Euler formula. So I'm going to use pi squared, actually I'm going to put in 3.14 squared, times 1,600,000 is the elastic modulus, times, now I need the moment of inertia in the smallest direction, so that's going to be the 5 by 8, so we're going to use the moment of inertia along this axis, so it's going to be 8 times 5 to the third over 12. Make sure I have the right dimensions. It is 5 by 8. So So 8 times 125 divided by 12. 83.33. So times 83.33 over L squared. We didn't give you the height of this, did we? Let's say this is a 10-foot high post. So that's going to be 120 inches, and that'd be squared. So we have 83.33 times 3.14 squared times 1,600,000 divided by 120 squared gives us, oofta, 91,000 pounds that it is able to carry in buckling. We're only loading it with 40,000. We should be good. What do you think? Now, there's something we need to discuss about these columns. It is the end conditions. With our beams, we always assumed that the beams were, we didn't really state it too often, but we always assumed that they were pinned on one end. So this end couldn't slide in and out, but it could rotate. It could pivot on that pin. And that it was on a roller on the other end. So that meant on this end, it could roll back and forth freely. And that's how we analyzed our beams. That was what's called a non-restrained condition. So that beam could move and flex and stretch and whatever, however it needed to. It wasn't restricted. We discussed briefly if you had both ends pinned or both ends restrained or embedded into something, that changes how the beam behaves. We can't, with conventional methods, we can't analyze that without using calculus. We don't want to use calculus. But that beam will be stronger than an unrestrained beam. So we just analyze it as though it's unrestrained, and we know that if it fits analysis, it survives, passes analysis as unrestrained beam, it'll be even stronger as a restrained beam. For columns, we tend to break it down and actually look at each of the possible end conditions. So we're going to go, starting on page 446 here, we're going to talk about the different types of end conditions. The end condition that we have discussed, the formulas I've given, the critical load, is for a beam or a post where both ends are pinned. What that means is they could rotate if they wanted to, but they can't slide or move. And that's where that critical stress formula of pi squared EI over L squared came from. This is the one we are going to assume for pretty much all of our analyses. That's not restrained, it's pinned. So it can pivot, but it cannot slide. Another case we could have, as we go through there on page 447, you can see we could have both ends fixed. Fixed means not only can they not slide, but they can't rotate either. They are fixed. And the critical load there is 4 times pi squared EI over L squared. So you can see this can actually handle 4 times the load without buckling. If you think about it, if you go up here, this post, if you think about it like this, is here's all your posts attached. Since this post can rotate at those 2 points, here and here, that post can buckle relatively easy. But if it is fixed on the ends, where it can't rotate right here or at the other end either. So what has to happen then for that beam to buckle is it stays straight here and it has to start buckling beyond that area that's controlled by the fixed end. Up here, this can start buckling immediately at the end because it can pivot. So with fixed ends, it is a stronger column, therefore it has a higher critical load. As you go through all of these formulas down through here, case C, one end pinned and the other end fixed, it's going to be 2 times the formula instead of 4 times. It's a higher critical load. Moving over to page 448, either it's equal to or higher in that first case where both ends are fixed with some lateral translation. The only 2 cases we need to worry about are cases D and F. Case D, one end is fixed and the other end is free. But that generally is the post is fixed into the ground. Maybe it's like buried into the ground and concreted in. But the other end is standing free. Maybe a birdhouse on top of it or a flagpole or something like that. Obviously, it's not going to have a heavy load, but because it's not held at all on the top here, it doesn't take much of a load to cause this thing to start bending off to the side. So the critical load there is pi squared EI over 4 L squared. I believe your textbook puts 1/4 on top instead of putting the 4 on bottom. Basically what this is it's 1/4 of the critical load you would normally have if both ends were pinned in our standard situation. And then, of course, the other case, case F on page 448, the bottom is pinned instead of fixed. And, of course, the top end then has to be somewhat fixed or it's not going to stand up. It's just going to flop over like a wet noodle. But there's still the ability to move with some lateral translation. And if that top can move from side to side, it can sag a lot easier. That's why it's very critical. Those beams often have blocks in the side of them to keep them from twisting or turning. Because if that beam starts to twist or turn, it allows that column, let's draw it out. Let's say the beam is sitting right here with that column underneath it. Well, if that beam starts to twist or turn a little bit, like this, now that column is allowed to move off to the side. And once that column starts to displace off to the side at all, then buckling can dominate very quickly. Any questions? So the only cases we have to worry about is if we have a post that has the top end that's free. The top end can move side to side. Then we have to worry about adjusting that formula to be 1/4. All the other cases, whether it's restrained or fixed, I should say, or not fixed, we're just going to use the formula for having both ends pinned, which is pi squared EI over L squared. That is the critical load for that post, for buckling. Any questions? So, I want to find the size of a post required to support 50,000 pounds, 50 kips. So our critical load is going to be 50,000 here. And let's say the post is a 12-foot post, 12 foot tall. So that means 12 feet is 144, so L squared will be 144 squared. 3.14 is still going to be pi. A wooden post, so E is still 1,600,000. It is I that's in jeopardy here. But if this is a square post with side X, the moment of inertia is X times X to the third or X to the fourth over 12. So we can use that to figure this out here. First of all, let's find what the moment of inertia has to be. To do that, I'm going to take the 50,000 here times 144 squared. Then I'm going to divide by 3.14 squared. And I'm going to divide by 1,600,000. So we have 65.72 is our required moment of inertia. But as we just found up here, since it's a square post, the moment of inertia is just x to the fourth over 12. So we're going to take that 65.72 times 12. And now we got to do a fourth root of it, x to the fourth. So we're going to do 4. On my calculator, I got to find the x root key. And then the previous answer. 5.3 inches is the minimum size of the side of the post. So use a 5.5 inch by 5.5 inch post. Or the nominal 6 inch post. What do you think? Fun stuff? The good news is that is the end of the new material for the semester. On page 455, have you work on 9.1 through 9.5. Analyze the columns. Starting next Tuesday, I will have a test for you guys to work on. I realize I've got to put the last 2 lecture notes out there for Blackboard as well. I'll get those put out there for you in the course materials. And then by Tuesday, I'll have the last unit test. It will not be a cumulative test. It'll just be a last unit. So it's just going to be on the beams and the shear and moment diagrams and column buckling and bending and all that good stuff. What I'll probably do is give you like 3 or 4 beams and ask you to do an analysis, step you through the diagrams and everything else. Any questions? Okay, I think you'll call that a wrap then.